audible? Can anyone please confirm?
Yes,
Yes,
ma'am.
ma'am.
Okay, thank you. Good evening, everyone. I am Riya Tatwal. I am doing PhD at IIT Kharagpur under the supervision of Professor Sudeep Mishra. Today we are going to discuss the topics of week 9, and after that we will discuss some questions. So in the last session we were discussing about cloud computing. We will continue with that only, and after that we will discuss about sensor cloud and fog computing. So first topic that we are going to discuss is OpenStack. So OpenStack is a software which is used to create a cloud infrastructure. It is launched as a joint project of Rackspace Hosting and NASA. It is open source, and presently many companies are contributing to OpenStack. Basically, it has very large community, and there are various versions of OpenStack available. So the last version which I have mentioned is Z, which was launched in 2022. So OpenStack has various components. So this figure is showing the different components of OpenStack. So first component is Horizon, then Nova, Glance, Swift, Neutron, Cinder, Heat, Ciliometer, and Keystone. We will discuss about these components one by one. So first component is Keystone. So a Keystone component is responsible for providing the identity service and provides authentication and authorization to various users. So with the help of Keystone component, the OpenStack can check whether the user who is trying to access it is authorized to access or not. So basically, it is used to provide identities to its various users. Second component is Origin. So this is the dashboard with the help of which you can access all the other components. It is the GUI of OpenStack and provides the overview of other components which are available. Then next one is Swift. So Swift is responsible for providing object storage. It helps in storing the data safely, cheaply, and efficiently. Next one is Nova. So this is responsible for providing computing services where you can launch your instances and run those. Then next one is Glance. Glance is responsible for providing image services. So, it helps in discovering, registering, and retrieving the VM. And with the help of snapshots, you can install different instances. Next one is Neutron. So Neutron is responsible for providing the networking service. With the help of Neutron, different services which are present can communicate with each other, and they can also make their own network. Next component is Cinder. So Cinder is responsible for providing block storage. It virtualizes the management of block services. Next one is Heat. Heat is responsible for providing orchestration to OpenStack. Then Ciliometer. Ciliometer is responsible for measuring the services which you are using, providing billing, and it also measures that for how long period you are going to use that particular service. So So basically two component that is Cinder and other one is Swift. These are responsible for providing storage. The difference is only that one provide object storage However, the Swift provide object storage. However, Cinder is responsible for providing block storage. Now, after OpenStack, we'll move towards Sensor Cloud. So, Sensor Cloud. So, what exactly is this Sensor Cloud? So, this word is made up of two words, that is sensor plus cloud. So, someone can think that it is the integration of sensor plus cloud. So, basically, taking the data from sensor and storing it into the cloud. So, one may think of like that. Other can think that it is dumping the data into the cloud, but sensor cloud is not exactly that. uh, it it consists of these two concepts, that is the integration of sensor and cloud computing and dumping the data of sensor into the cloud. However, apart from that, the concept of sensor cloud consists of virtualization. So basically similar to cloud computing, where we have various resources and these resources are virtualized. Basically a single resource can be used by different users, and the user are not aware that this resource is shared between them. So similar to that only, in sensor cloud, a particular sensor may be used by different user. However, the end users are not aware of that particular thing, that that sensor is used by different end user. So in sensor cloud also, like in cloud computing, there is paper use concept. So basically the amount of sensors you are using for the particular period of time you are going to use that particular sensors, you have to pay for that. One sensor node appears as many. So basically one sensor nodes can be used by many end users, and for those end user it seems that they are using different sensor. A stratum between sensor nodes and end user is there. So one computer host appears as many computers concept of virtual machine. So basically this is the cloud virtualization concept. So in cloud virtualization, one host may appears as different with the help of virtual machine concept. It improves the IT throughput and cost by using physical resources as a pool from which virtual resources can be allocated. Now, what are the benefits of this virtualization? So first benefit is sharing of resources. So same resources can be shared in term of cost reduction. So basically a particular resource is shared by many users, so this will results in reducing the cost. Sorry. Second one is encapsulation. So a complete computing environment is provided to the end users, and they are not aware of that basically that particular sensor or particular resources are used by others also. Third one is independence. So run independently of the underlying hardware. Next one is portability. So you can migrate the virtual machines from one device to other. Now here this table is showing the difference between the traditional wireless sensor networks and the sensor cloud. So in case of traditional wireless network, the ownership of sensors is the sensor user basically. So for example, you are going to deploy some application in case of the WSN, then you have to own those particular sensor which you require. However, in case of if you are going to use sensor cloud, you don't need to own your own sensors, right? You can use the sensors which are owned by the sensor owner, and further you have to pay for these sensors. Next one is deployment. So in traditional WSN users are responsible for the deployment. However, in case of sensor cloud, sensor owners are responsible for the deployment of these sensors. Then redeployment also, WSN users are responsible, and in case of sensor cloud, service providers are responsible. Then maintenance. WSN users are responsible. However, in case of sensor cloud, service providers are responsible. Then for overhead charges, WSN users are responsible. In case of sensor cloud, service providers are responsible. Then usage, WSN users are going to use those particular sensor. However, in case of sensor cloud, end users are going to use those the facilities which are provided by those sensors. Now this figure is basically showing the difference between the traditional WSN and the sensor cloud. So basically, in case of traditional WSN, there are various sensors which are deployed. So for example, you want to monitor your agricultural field, okay, so you have deployed various sensors, for example, a PIR sensor, ultrasonic sensor, camera sensors, right? So basically, in order to detect whether some intruders are going to enter into your agricultural field or not. So basically, these sensors are going to collect the data and send to the end users, right? Now, this is the case of WSN, where different sensors are going to collect the data and send to the end user. However, in case of sensor cloud, so for example, you have used this camera sensor in your agricultural field, right? So this camera sensor can be used for other applications also in that particular area, right? So basically, in case of sensor cloud, the sensors which you have deployed can be used by multiple applications or multiple users. However, in case of traditional WSN, only a particular application for which you have deployed the sensor that can use that. Now the components of sensor cloud. Now the components of sensor cloud, basically the actors which are responsible for the working of this sensor cloud. So first one is end users. So end users are the user who are going to utilize or use the facilities which are provided by your sensor. So they are unknown about what and which physical sensors are allocated to serve the application. Next component is sensor owner. So sensor owner plays a role from business perspective. They purchase their own sensor, deploy for a particular application, and they are going to charge from the end user for the facilities which these sensors are providing. So basically, they purchase physical devices, deploy them over different geographical locations, and lend these devices to the sensor cloud. Now the next component is sensor cloud service provider. So it is a business sector which charges prices from the end user as per their usage of the sensor as a service. So some example of sensor cloud service provider include AWS IoT, Microsoft Azure IoT, Google Cloud IoT, and IBM Watson IoT. Now the architecture of sensor cloud. So basically we discussed about three components, that is end user, sensor owners, and service provider. So this is a figure showing the architecture. So basically the first layer is of sensor owners. So basically these sensor owner own their sensors. They deploy these sensors into the geographical location, and further this service provider are responsible for pricing, caching, composition management, and virtualization of these physical sensors. So basically, for example, consider that this red sensor, blue sensor, and yellow sensor, right? So service provider can make a one logical sensor of all those three, or on the other hand, it can also create many instances of a particular single physical sensor. For example, for this red colored sensor, it can create 3 instances. So creating 3 instances means 3 different users can use that particular single sensor. And on the other hand, there might be a chance that a single user is using 3 different sensors. So in that case, 3 sensors make one logical sensor, and on the other hand, there might be a chance that one physical sensor is going to create 3 logical sensors. After that, the third layer is end users. So basically, end users are going to use the facilities which are provided by these sensors. So first of all, end user register themselves, select particular templates, and then request for the particular kind of application. After that, sensor owner deploy heterogeneous as well as homogeneous physical sensors over a particular geographical location, and SP, that is your sensor cloud service provider, are responsible for the managerial role. Managerial roles means these all facilities are provided by your SCSP. Then management issues that can occur in sensor cloud. So first one is optimal composition of virtual sensor nodes. So optimal composition of virtual sensor nodes means for a particular kind of application, how many sensor nodes are required, or how many virtual sensors we can create from a single sensor. So taking this decision is one of the major issue. Second one is data caching. So sometimes there are things that environment does not change very frequently. So in that case, taking data from sensors regularly will result in the wastage of energy, right? So in that case, in order to prevent that, we can cache the data and use that particular cache data. Now the problem is that when to refresh that cache. So when to take the data from the sensor and recache your cache memory. So this is one of the issue. Next one is optimal pricing. So optimal pricing means considering that for different kind of sensor, how much price will you take, for how long period you will take, how much amount. So that is your optimal pricing. So this is the sensor cloud view. So basically here this is the user organization view. However, this is your real view. So if you are going to see from your end user point of view, so there are various applications, right? So these applications are going to interact with the sensors through the browser interface. So first of all, the user will log in through your browser interface. Then different templates were displayed to the end user. The end user will select one of the template, and depending upon the template specification, the sensed information will be sent to the user. However, on the real view, this is basically end user point. So end user just see a web browser. So through that browser only that can access the data. The end user does not know the physical sensors which were deployed, how these sensors are sending the data, how many sensors they are using. So end user does not have any idea about that. So in a real view, what happened is, this is the web portal. So template specification which is selected by the end user is sent. Now depending upon that template specification, that the service providers which are there take decision and send the data from the physical sensor to that particular application. now. So these are the various decisions that should be taken at in your virtual sensor. So first one is efficient virtualization of physical sensor node, that how you are going to virtualize your physical sensor, how many instances should be created of your physical sensor. Second one is an optimal composition of virtual sensor. Optimal composition means if you are going to create a single logical sensors from multiple physical sensors, that then the second challenge is which kind of sensor you are going to take, how many sensor you are going to take. So this is an optimal composition of VS. Third one is consider same geographic region. So sometime when you are creating a virtual sensor, you are going to consider same geographical region. However, in some cases you are going to deploy your sensors over multiple regions. Yeah, so basically here in the first figure, only in order to create one virtual sensor, only homogeneous kind of sensors are used. So for example, here 5 sensors are used in order to create one virtual sensor. However, in this second figure, different kinds of sensor are used in order to create virtual sensor. For example, VS1 is made up of these different kind of sensors, right? And these different kinds of sensors are also not present in the same geographical region. These are present in different geographical region. So depending upon the requirement of your application, you can decide whether you are going to use a homogeneous kind of sensor in order to create your virtual sensor, or whether you need heterogeneous kind of sensors in order to generate your virtual sensor. And also the location that where you are going to deploy your sensor is also dependent upon the application scenario where you are going to use this. So this is the so first one is the formation of virtual sensor. So optimal formation of virtual sensor, so it can be either homogeneous from same geographical boundary, or it can be heterogeneous from different geographical location. Now, why composition of virtual sensor? So basically, why do you need virtual sensor? Why do you need different kinds of sensors in order to create one virtual sensor? So the reasons are, first one is resource constrained sensor node. So basically, if you are going to use single sensor only, so as we know that the sensors are resource constrained. So to prevent this problem, you can use different sensors and create one virtual sensor. Second one is dynamic change in sensor condition. So sometimes there is a possibility that one of your sensor get malfunctioned, or due to some environmental condition it is not working fine, right? So in that case it is not going to give you the correct information, or it is not going to sense the correct data. So in that case, if you are using different sensors, then the chances of this incorrect values will get reduced. The next one is the compositions of virtual sensors are non-traditional here. So in non-traditional wireless sensor nodes, this composition of virtual sensors is not there. After that, dynamic and adaptive caching mechanism. So it introduces two types of caching mechanism. First one is internal and second one is external, which ensures efficiency in resource utilization and also the flexibility with the varied rate of change of the physical environment. So why caching in sensor cloud? So why do you need to cache the data? So first reason is end user request for the sensed information through the web interface. The allocation of physical sensor nodes and virtualization take place as we have discussed in the previous slide. Then physical sensor nodes continuously sense and transmit the data to sensor cloud. Practically, in some cases, the change in environmental condition is significantly low. So basically, this is the main reason that why you need caching in the sensor cloud. That's the change in the environmental condition in some cases is very low. So in those scenarios, if you are continuously getting the data from your sensors, then it will result in the wastage of energy, and the lifetime of sensors which are involved in sensing will get reduced. So due to the slow change in environment, the sensed data of physical sensor remain unaltered. In such a situation, unnecessary sensing causes energy consumption, and in order to prevent that, you need to cache the data. So now this caching is of two types. First one is internal caching, second one is external cache. So this internal cache is responsible for handling the request from the end user, and it takes decisions whether the data should be provided directly to the end user or is it required to recache the data from external cache. Basically, depending upon the requirement of the end user, this internal cache will decide whether the data which is stored is fresh or do we need to get the data from the physical sensor. The second one is external cache. So external cache is responsible for recaching after every regular interval of time. So after every certain interval of data are required to recache. Initially few data are used to be transmitted to the internal cache in this case. So this figure is showing the difference between the existing architecture, that is without caching and with caching. So first one is without caching. So in case of without caching, every time your end user want data, that is your application want data, your sensor cloud is going to take the data from the physical sensor and further send it to the end user. However, in case of cache enabled architecture, whenever your applications want data, so this internal cache will decide whether to provide the data from this internal cache only or whether to take the data from the sensor cloud or from the physical sensor. So basically, if the data present here is relevant, it will directly give the data to the end application. So basically in that case, the time required to send the data to the end user will also get reduced. Okay, and further this external cache, after every regular interval of time, it is going to store the new data into your cache memory. Now dynamic optimal pricing for sensor cloud infrastructure. So existing scheme consider the homogeneity of the services. There is no scheme present for sensor as a service. So the proposed pricing scheme comprises of two components. First one is pricing attribute to hardware, and the second one is pricing attribute to infrastructure. So pricing attribute to hardware is PH and pricing attribute to infrastructure is PI. So the goal of this proposed pricing scheme is to maximize the profit of your SCSP, that is your sensor cloud service provider, maximizing the profit of sensor owner, and maximizing the facilities or satisfaction of the end user. So it basically focus on maximizing the profit made by SCSP, optimal pricing to the end user. End user satisfaction is important. Then pricing attribute to hardware deals with the uses of physical sensor node. However, pricing attribute to infrastructure deals with the price associated with the other infrastructure which is required in order to establish your sensor cloud. Give me 1 second. So basically this figure is showing that how pricing and negotiation is fixed at your service provider end. So basically these are different end users who wants to use the facilities which are provided by the sensors. These are the sensor owners which deploy different kind of sensors. So these sensor owners want to price for these sensors. So basically this sensor cloud is responsible for the pricing and negotiation. Now the next topic is fog computing. So fog computing or fogging is a term coined by Cisco. The idea of fog computing is to extend the cloud nearer to IoT devices. So basically it means that the services which are provided by your cloud, so to bring those services near to your end devices, right? So consider a scenario. So basically, okay, so for example, if you want to purchase something, right? So consider that the Amazon main server is present in USA, right? So if you want to purchase something, then every time you want to search for an item, your request will be sent to USA. In case of cloud, I am saying your request will be sent to USA, their processing will take place, and after that the response will be sent. So in that case, the time taken in order to send the request, to process, and further to send back the response is large. So the main concept of fog computing is to bring down this service near to your place only. So for example, if you are in Kharagpur, right? So to place the server near to your place only. So basically there is one sub server which is present in the Kharagpur. Main server is at your USA. So basically depending upon depending upon the need of a particular place. For example, if someone is staying in Kharagpur, so their preferences of clothes will be different from those who are staying in Mumbai, right? Or someone who is staying in Himachal, their preference of clothes is different from those who are staying at Kharagpur. So better to save or store those items near to the end user. For example, see, if I am in Kharagpur, so the preferences or the type of clothes which I want will be stored in the server which is placed at Kharagpur. So this is the main concept of the fog computing. So the primary aim is to solve the problem faced by cloud computing during your IoT data processing. An intermediate layer between cloud and devices is present in case of your fog computing. So this intermediate layer is your fog layer. So the example is same as I am the end user. some sub-server is placed at Kharagpur, that is the intermediate layer, and the main server which is present in USA will be the cloud. Then 40% of the whole world's data came from the sensor alone by 2020, and 90% of the world's data were generated only during the period of last 2 years. So this is the data of 2020. So basically, in case of IoT, when you are using IoT, you need fast processing. So for example, in case of smart vehicles, you need to process your data very fast within milliseconds, because if there is some delay, it may result in accidents also, right? So in that case, you need processing very fast. You want your response in within a very less amount of time. So for that purpose, you need a particular layer near to the end user. So that's why fog computing was introduced. So 2.5 quintillion bytes of data is generated per day. Total expenditure on IoT devices will be $1.7 trillion by 2020, and the total number of connected vehicles worldwide will be 250 millions by 2020. There will be more than 30 billions of IoT devices, and the amount of data generated by these IoT devices is simply huge. So basically, in order to manage this data and in order to process this data, you want a particular intermediate layer which is going to process this data. Now, why fog computing? So the ability of current cloud model is insufficient to handle the requirement of IoT. The issues with the current scenario is volume, because the data which is generated by these billions of IoT devices is very huge. Second one is latency, because the distance between the end users and the server, cloud server, is very large, and the latency involved is to send the request, processing, and send back the response. So it is very large, and if you are going to send that huge amount of data, the bandwidth which is required in order to send this data to your server is high. So in order to reduce these problems, or in order to solve these problems, there is a need of intermediate layer. So first one is data volume. So yeah, so you can read these points. This is nothing but that the data which is generated. So basically, I have already discussed. So to process the data which is generated by IoT devices, you need a one particular intermediate layer. Yeah. So latency. So latency means the time taken by data packet for a round trip. So to send the request, then processing, and send back the response. This is your latency. And it is an important aspect for handling a time sensitive data. If edge devices send time sensitive data to cloud for analysis and wait for the cloud to give proper action, then it can lead to many unwanted results. While handling time sensitive data, a millisecond can make a huge difference. Sending time sensitive data to cloud for analysis involves these different times. So first one is time to send the request to the cloud, then the time required for data analysis, and the time used to send back the response. So latency will be increased if you are going to use traditional cloud model. When the action reaches the device, there may be chance that accident may have already occurred. So in order to solve this problem, you need a one particular intermediate layer. And the next one was bandwidth. So bitrate of data during the transmission is your bandwidth. If all the data generated So if all the data generated by IoT devices are sent to cloud for storage and analysis, then the traffic generated by these devices will be simply very large. It consumes almost all the bandwidths. Handling this kind of traffic will simply is a very hard task. So basically there are billions of devices which are consuming the bandwidth, and if all the devices become online, even IPv6 will not be able to handle or provide facilities to these devices. Now the requirements of IoT. So the first requirement of IoT is to reduce the latency, because in case of IoT you need the processing to be very fast. So appropriate actions at right time prevents major accidents, machine failures. A minute delay while taking a decision make a huge difference. Latency can be reduced by analyzing the data close to your data source. Second one is data security. So if you are going to use cloud, you have to send your data to the server which is located very far from the end user point. So there might be a chance that your data may be corrupted when you are sending the data to the cloud. Also there might be a chance that attackers might attack on your data. So IoT data must be secured and protected from the intruders. Data are required to be monitored 24/7, and an appropriate action should be taken before attack cause major harm to the network. So this can be done easily if your data is stored near to the end user, and also it becomes easy to manage your data if it is near to the end user. Then next one is operation reliability. So the data generated from IoT devices are used to solve real-time problems. Integrity and availability of data must be granted. Then unavailability and tampering of data can be hazardous. Processing of data at respective suitable places is required. Extremely time sensitive data should be analyzed very near to the data source. Data which are not time sensitive will be analyzed in the cloud. Next one is monitor data across large geographical area. So the location of connected IoT devices can be spread across the large geographical regions. For example, monitoring the railway track of the country or a state. So in this case, your sensors are deployed over a large location, and devices are exposed to a harsh environment condition also. So when should we use fog? So if the data should be analyzed within a fraction of second, then you should use fog. If there are huge number of devices, then fog should be used. If the devices are separated by large geographical distance, then you can use fog. If the devices are needed to be subjected to extreme condition, then you can use fog. Now the architecture. So this figure is showing the architecture of fog fog computing. So basically the lowest layer is the IoT layer, which consists of physical sensors or physical devices, IoT devices. Then the next layer is the fog layer, where various fog nodes are present, and on those fog nodes various fog services are present. So these services are similar to the services which are provided by cloud only, but these services are basically present near to your IoT devices. And the third layer is the cloud. So in case of your fog computing, cloud services are extended to IoT devices through fog. Fog is a layer between cloud and IoT devices. Many fog nodes can be present. Sensor data are processed in the fog before it is sent to the cloud. It reduces latency, save bandwidth, and save the storage of the cloud, because some data is stored at your fog. Then the fog nodes. So what should be the characteristic of your fog node? So first one is storage. So basically it should provide transient storage. Then computing facility should be there. So there should be some facility to process your data near to your end devices. Then these fog node should have network connectivity. So basically in order to connect these devices to your end devices and also to the cloud, there is a requirement that these nodes should have network connectivity, and each fog node have their aggregated fog node. So basically for example, there are various fog nodes, so there should be one aggregated fog node which is going to send the data further to the cloud. Now the working of fog. So before discussing the working of fog, we will discuss the three types of data. So first one is very time sensitive data, which need to be processed within a few seconds of time. Second one is less sensitive time data, which can be processed, which can tolerate some delay, and the data which is not time sensitive at all. So you can process this kind of data if in large time amount also. So fog nodes work according to the type of data they receive. An IoT application should be installed to each fog node. The nearest fog node ingests the data from the devices. So if the data which is most time sensitive, then the fog node which is closest to IoT device is going to process that particular data and send back the response to IoT device. And if it is, so there might be a chance that the fog node which is near to your end device is busy, right? And if that particular fog node is receiving a data which is not that time sensitive, which is less time sensitive, so it may send that particular data to other fog node also, which is not near to the end device which is sending the data. And if the data which is received by the fog node, the closest fog node, is not time sensitive at all, then that particular fog node is going to send the data to the cloud. Okay. So basically this figure is showing that your end devices are going to send the data. The nearest fog node, if the data is most time sensitive, then it is going to process that data, or there might be a chance that this device is busy. So if it is very time sensitive, then this device is only going to process that data. And if it is less time sensitive, then this fog node is going to send the data to some other fog node, and that particular fog node is going to process the data and send back the response to the nearest fog node, and further this nearest fog node will send back the to device. And if it is not time sensitive at all, then the data is sent to the cloud for processing. So this table is showing the working of fog only. So fog node which is closest to the device, so the analysis duration for this is fraction of second. The aggregate fog node, it can analyze the data from seconds to, it can take time from seconds to minutes, and for clouds it may be hours to weeks. Now IoT data storage duration. So it is very transient. So after every regular interval of, or after very short interval of time, the data will be replaced. For aggregate node, it may be for hours or for days, and for cloud, it is for months to years. Then the geographical coverage for the closest is it's very local. For aggregated nodes, it's wider, and for the cloud, it's global. Now the advantages of fog. So first one is security. It provides better security. Fog can use same security policy as used by cloud. But since your fog devices are near to your end user, so there are less chances that the data will get corrupted. Next one is low operational cost. So data are processed in fog nodes before sending it to cloud. So it reduces the bandwidth consumption, which results in low operational cost. Then next advantage of fog is it reduces unwanted accidents, because the decisions are taken place at near to your end devices, so the latency will be reduced. Quick decisions are taken, so which results in minimizing the unwanted accidents which happen due to your latency. Third one is better privacy. So every industry can analyze their data locally, store confidential data in their local server, and send only those data which can be shared to the cloud. Third one is business agility. Fog application can be easily deployed according to the tools available. It can be deployed anywhere we need and can be programmed according to the consumer need. Next one is sport mobility. So fog nodes can be mobile and can join and leave the network anytime. Then deployable in remote places. So it can be deployed in remote places, can be subjective to harsh environment condition. So fog nodes can be deployed under sea, railway tracks, vehicles, factory floors, etc. Next one is better data handling. So your fog nodes can operate with less bandwidth. Data can be analyzed locally and it reduces the risk of latency. Now the applications of fog. So first one is real-time health analysis. So in case of your hospitals, you can use fog nodes for providing real-time health analysis. So patients with chronic illness can be monitored in real time with your fog computing. So it analyzes the data in real time, so during emergency alerts and respective doctors can immediately be informed, and historical data analysis can predict future dangers that can happen to patient. Then for intelligent power system, you can use fog. Then for real time windmill and turbine analysis, real time rail monitoring, pipeline optimization, you can use fog. So basically fog can be used in those applications where you need your data to be processed in very less time. Then the challenges. So first one is power consumption. So basically in case of fog, you are going to deploy extra nodes which are going to consume some extra amount of energy. So power consumption is one of the biggest challenge of fog. Second one is security. Since in case of fog computing, basically fog nodes are not that much, do not have that much resources as of cloud, right? So they are not able to provide that much security to your end user which is provided by the cloud. So the data which is stored at the fog node are maybe more prone to corruption as compared to data which is stored at cloud, because in cloud you can run various kinds of algorithms which are not supported by fog in order to secure your data. Then reliability, and then the next one is fault tolerance. So if your node will get faulty, failure of node should be immediately fixed. In case of your fog computing, individual failure should not affect the whole scenario. Then the programming architecture, so fog nodes may be mobile, nodes can connect and leave the network when necessary. Many data processing framework are statically configured. These framework cannot provide proper scalability and flexibility. Next one is real time analysis. So in case of fog, you need a real time analysis. Dynamic analysis and decision making reduces the danger and increase in output. It monitor huge number of nodes is not easy in this case. Yeah. So before discussing questions, so I'll also discuss about edge computing. I'll just give you a brief idea. So like fog, there is one more layer which is introduced between the end devices and the fog. So basically, yeah, this is the architecture of fog, right? So these are the IoT devices, there is fog layer and there is cloud layer. So in case of edge computing, there is one more layer between your IoT device and your fog. So in that case, the services which are provided by fog or cloud are brought more nearer to your end device. Basically, that processing will take place on the end device only. So for example, you are using smartphones, right? So sometime when you are typing something over your mobile, it is predicting the next word, right? Because depending upon the chat which we made previously, or depending upon the search which we made previously, it is going to predict the next word or next sentence, right? So this processing is done on the same device, right? So this is called edge computing. So in case of edge computing, this processing and analysis is bring down over your own devices. So basically, IoT device here means the sensor which are present over your mobile, and then that mobile or the device which is same your mobile phone is going to do some processing, and then it is sending to the fog layer, or it will send the data to the fog layer and further to the cloud. So depending upon the sensitivity of data, the processing will take place. So if it is more sensitive, the processing will take place at the edge layer, that is on your device only. If it is less sensitive, it is sent to the fog layer, and if it is not sensitive at all, then the data will be sent to the cloud. And nowadays there is one more layer introduced, which is sky. So sky is above cloud. So in case of sky computing, the interoperability of different kind of clouds. So basically, there are different kinds of clouds, right? And the services which are provided by different kind of clouds are different. So in order to provide standard services to the end user, or your end user will not get to know that from where they are getting services, there is a need to provide interoperability between different kind of clouds. So this sky computing is responsible for providing that. So that sky layer is placed above your cloud. So basically, logically you can think IoT layer, then edge computing layer, edge layer, then fog layer, then cloud layer, and now sky layer. So basically 5 layers. There are now 5 layers. Okay. So this fog computing and cloud computing, these are now obsolete, not obsolete, but lots of research has already been done on these two layers. Nowadays, edge computing or edge intelligence is in trend. So providing processing over your edge devices, is in trend. So how to use machine learning model over your edge device, because the processing power of your edge device is very less as compared to the fog devices and cloud. So running machine learning models over your edge device is one of the challenge. How to make lightweight machine learning model so that they can be run over your edge device. This is one of the hot research topic nowadays. Second one is sky computing, to make the interoperability possible between different cloud. So this concept sky computing, I guess it was coined I guess in 2020 or 2021 only. So it is very new and only few research has been done in this area. Yeah, so before starting to the questions, let's take a break of 5 minutes, and after that we'll start with questions. Can you explain the term benefit with example? Which benefit can you please explain? I'm not getting your question. Link, okay. This is the link. I have already uploaded the PDF. You can check. Vinayak Deshmukh, I'm not getting your question. What exactly you want to ask? I'll start the question after 5 minutes. question is, can we say multi-cloud deployment as sky computing? No, there is a difference between multi-cloud deployment and sky computing, because multi-cloud deployment is already there, right? So multi-cloud deployment means for a particular kind of applications you are using different cloud, or you are using different service providers which are providing the same services or different services, right? So depending upon your need, you can use a service from either one provider or other. However, in case of sky computing, this choosing is shielded. Basically, there is one intermediate layer which will uh, uh, make, so basically end users will not get to know that from which particular cloud you are accessing the service. So in case of multi cloud, your end user is going to choose the particular service provider depending upon his need. However, in case of your sky computing, there is one layer which is automatically selecting the best service provider for you. So yes, in case of sky computing, there are multiple clouds providers which are providing you the services, but there is one layer which is automatically selecting the best possible service provider for you. However, in case of your multi-cloud, you are going to select the service provider depending upon your need manually. PPT I have shared. I'll share the link again. So this is the link. If you want to explore sky computing more, there is one researcher whose name is Ion Stoica. I'll write his name. He is from University of Berkeley, California. So he only coined this term sky computing, and he just started one lab, that is sky computing lab. He has various research paper, so you can go through these research papers if you want to explore more sky computing. Okay. So now the questions. First question is, OpenStack is proprietary and a closed source software that you have to pay and buy. Options are true or false. Anyone?
Option B, false.
False. Okay. Anyone else? False. Anyone else? Right. This statement is false, because open source, OpenStack is open source and requires no payment. Next question is, in OpenStack, which of the following component take care of user authentication? Options are Nova, Origin, Keystone, none of these.
B, horizon.
B. Okay. Anyone else?
Keystone.
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 Anyone else?
Keystone.
Yes, Keystone Next slide. Keystone is responsible for providing authentication and user authorization. However, your origin is the dashboard, which provide access to your different components of OpenStack. Next question is, you cannot ping your OpenStack instance from an outside network unless you connect your instance with the public network through a blank. Options are router, firewall, repeater, load balancer.
Option A router.
Option A, router.
Okay, anyone else? Yeah. Right, so correct option for this is router. Next question is, what is primary service model for a sensor cloud? Options are hardware as a service, platform as a service, data as a service, sensor as a service.
Option D, sensor as a service.
Anyone else?
Sensor as a service. Option D.
Option D, sensor as a service. Right, so correct option for this is sensor as a service. Next question is, you can run two logical computers, one Linux machine and one Window machine on top of same physical hardware through the use of options are sharing, scaling, virtualization, inheritance.
Option C, virtualization.
Okay, anyone else?
Virtualization. Option C.
Yeah, so correct option for this is virtualization. Next question is, in sensor cloud, one physical sensor can be abstracted as multiple virtual sensors. True or false?
Option A, true.
Okay, anyone else? Right. So the correct option for this is true, because in case of your sensor cloud, either you can abstract one physical sensor into multiple virtual sensors, or on the other hand, you can aggregate various physical sensor in order to create one virtual sensor. So this statement is true. Next question is, in a sensor cloud framework, the end user have to continuously worry about owning and managing the physical sensor devices. True or false?
It's option B, false.
False, ma'am. Option B.
Anyone else? True, false. So this statement is false, because in case of your sensor cloud, Your this service provider are responsible for managing the sensors, and this owning thing is done by the sensor owners. Next question is, virtual sensors within a sensor cloud have communication interfaces with blank. Options are: A is only the physical sensor below them, only the end user application above them, both physical sensor below and application above, neither the physical sensor nor the application. Anyone?
It's option C.
Option C, both physical sensor below and application above.
Okay, anyone else? Yeah, it's option C. So basically, in case of your sensor cloud, your virtual sensor is the intermediate layer, uh, which can communicate with the physical sensors also, and also the applications. Next question is, which of the following is true? First one is, traditional WSN support virtualization. Sensor cloud also support virtualization. B is, traditional WSM does not support virtualization, whereas sensor cloud support virtualization. C is, traditional WSM support virtualization and sensor cloud does not support virtualization. D is, traditional WSM no virtualization, sensor cloud no virtualization.
It's option
It's
B.
option B. Okay, anyone else? Anyone? Question is, which of the following is true? Traditional WSN virtualization support, sensor cloud virtualization support. B is, traditional WSN no virtualization, sensor cloud virtualization. Traditional virtualization, sensor no virtualization. Traditional no, sensor cloud no virtualization. Correct option for this is B, that is, your traditional wireless sensor does not support virtualization, however your sensor cloud support virtualization. Next question is, an organization ABC wishes to have uh, environmental monitoring parameters of a particular region but does not have the resources to deploy its own physical sensors. However, another organization B has some physical sensor that monitor environment deployed in that region. Can sensor cloud help achieving A's objective? Yes or no?
Yes. Yes.
Yes.
Option is.
Option is. Anyone else? Yes. Anyone else?
Option A
Option
S.
A is. Yes. So correct option for this is yes. Next question is, Referring back to question number 10, that is this question, this statement, and based on your answer, determine the roles that organization A and B plays in the scenario. Option A is sensor owner and B is end user. B is A is end user and B is sensor owner. C is both A and B are sensor owner, and D is both A and B are end user. So this is the statement. You can read and tell me that whether A is sensor owner or B is sensor owner, or both are sensor owner, or both are end user. Anyone? Have you read the statement? Basically, A does not have sensors and B have physical sensors. Now you have to tell whether A is sensor owner or B is end user, or exactly which one is end user and which one is sensor owner.
Option B.
Option B. So A is end user and B is sensor owner. Right. This option is correct because A does not have sensors, so it is basically going to use the sensors which is provided by B. Next question is, which among the following is limitation of cloud computing? Options are on demand services, virtualization orchestration, large amount of computing and storage resources, additional communication latency for critical application.
Option B.
Option, can you please repeat?
Option D.
Option D.
Okay, anyone else? Yes, so correct option for this is D. So in case of cloud computing, additional communication latency is there for which is not suitable for your critical applications. Next question is, in fog computing, the fog layer acts as an intermediary between the data source and the cloud for intermediate processing of time critical data. True or false?
Option A. True.
True. Okay, anyone
True.
else? Yes, this statement is true. Basically, fog layer is the intermediate layer which brings down the services which is provided by the cloud near to the end user. So this statement is true. Next question is, suppose that one-way communication latency from the device to fog layer is 20 millisecond and that from the device to cloud layer is 50 millisecond. Data processing time at fog is 10 ms and that cloud is 5 ms, after which a reply is sent back to the device by the fog or cloud What is the difference between the total communication latency between the device and the cloud and the fog respectively? Options are 50 ms, 60 ms, 55 ms, 100 ms. Okay, use your copy pen. Tell me the answer. Solve this and tell me the answer.
Option D 100.
Option
D 100.
100. Okay, anyone else? How did you solve? Can you please tell me that how you solved this?
Just making the difference between processing and latency timing.
Yeah, so basically for your cloud, one-way communication latency to no. So for cloud it is 50 millisecond, right? So one way is 50. So basically two-way will be 100 ms, and the processing time is 5 ms. So total is 105 ms for cloud. And for fog it is 20 for one time, 20 for coming back response, so it is 40. And the data processing time is 10, so total is 50. So the difference will be 105 minus 50, so it should be 55. Got my point or should I repeat? Anyone else who solved this?
55 milliseconds.
Yes, 55 milliseconds. So basically the total time is the time to send the request, then the processing time, and the time to send the response. So the time to send the request and response will be same. So for cloud it is given as 50. So for sending request 50 millisecond, for getting response it will be 50. So 50 plus 50 is 100, and the processing time is given as 5 millisecond. So total time which is required for cloud processing is 105 millisecond. And on the other hand for fog it is the time to send the request is 20 ms, time to get the response is 20, which will become 40, 20 plus 20, and the processing time at fog is 10 millisecond. Okay, so 40 plus 10 is 50. So for cloud it is 105 and for fog it is 50. So the difference is 105 minus 50, which is 55 millisecond. Okay. Next question is, which among the following is true? Option A is fog computing act as a complement to cloud computing. B is fog computing is a replacement of cloud computing. C is fog computing and cloud computing are the same. Fog computing is more powerful than the cloud computing.
It's option A. Fog computing acts as a complement to cloud computing.
Okay, anyone else? Someone is saying D, that fog computing is more powerful than cloud computing. How? How it is more powerful? Can you please explain that how fog computing is more powerful than cloud computing? Correct option for this is A, that is fog computing act as a complement to cloud computing, because in case of fog computing one extra layer is added which work along with your cloud computing. And option D is not correct because the fog nodes are less powerful, or they have less resources, they have less processing power as compared to your cloud. So basically fog computing is not more powerful as compared to your cloud computing. Next question is, the OpenStack cloud simulation framework provides an interactive GUI. True or false?
Option A. True.
True. Okay. Anyone else? A. True. Okay. And what is the name of that GUI? Anyone? What we call the GUI of OpenStack? No? Check your notes and tell me. No? I have given you the option of checking your notes also. I have provided the slides in the link also. You can go through that. Tell me what we call the GUI of OpenStack.
Horizon.
Right, it's Horizon. Next question is, virtualized resources within the OpenStack simulator that you can define, set parameters of and deploy within OpenStack are also known as, options are instances, files, hypervisor, sketches. you find the answer of this question, I am coming back in 2 minutes. Okay. So the question was virtualized resources within the OpenStack simulator that you can define, set parameters of, and deploy within OpenStack are also known as options are instances, file, hypervisor, sketches. Anyone? Am I audible? Question number 17B. Files. Okay. Anyone else? Hello, am I audible or not?
It's instances.
Instances. Okay.
Instances is the answer.
Yeah, right. Instances is the correct answer. Next question is, if you want to connect your OpenStack instance with the external public network, you would need to connect the following between your instance and public network. Options are database, memory, file, router.
It's option D, router.
Router. Okay, anyone else? Yeah, correct option for this is router. Next question is, which among the following is not a part of a sensor node connected to a wireless sensor network? Options are sensing unit, gaming unit, processing unit, communication unit.
Gaming unit.
It's option B, gaming unit.
Gaming unit. Okay. Anyone else? Yes, the correct option for this is gaming unit. Next question is, consider that you have two types of sensor: soil monitoring sensor for smart farming and temperature sensor for smart industry. The concept that the correct type of sensor must be deployed only at their correct and appropriate physical location suitable as per their functionality is known as. Options are right way of deployment, right place of deployment, right time of deployment, none of these.
Right place of deployment.
Which one? Option
D. Option D.
B, right place of deployment. Okay, anyone else? Yes, so correct option for this is right place of deployment. Next question is, sensor as a service is an exciting new concept that brings the service models of cloud computing to traditional IoT sensor network. In this aspect, which among the following forms an essential component of sensor as a service architecture? Options are sensor marketing, sensor division, sensor virtualization, sensor manufacturing.
It's sensor virtualization.
Sensor virtualization. Okay. Anyone else? Anyone for this question? Sensor as a service is an exciting new concept that brings the service model of cloud computing to traditional IoT sensor network. In this aspect, which among the following forms an essential component of sensor as a service architecture? Options are
Option C.
sensor
Sensor
marketing,
visualization.
virtualization. Okay. Yes, so correct option for this is sensor virtualization. Next question is, considering the end-to-end architecture of WSN from physical sensor node right up to the user, sensor clouds support different entities to have ownership of different layers and components simultaneously. True or false?
True, true.
True. Okay, anyone else? Anyone? Correct option for this is true. Next question is, in sensor cloud architecture, the sensor cloud service provider is logically situated at the following position of the architecture. Option A is in the same level as physical sensor, B is in between physical and user layer, C is at same level as the users, none of these.
Option B, in between the physical sensor and user layer.
Okay, anyone else?
It's option B, in between.
Right, option B is correct. So basically your service provider sits logically, it sits between your end users and your physical sensors. Next question is, in sensor cloud, the association between virtual sensor instances and corresponding physical sensor follows one to one mapping, one to many mapping, many to one mapping, many to many mapping.
One to many.
Many to many. Okay, anyone else? No? One to many. Anyone else? Correct option for this is many to many, because your in case of your sensor cloud, one single physical sensor can be taken as multiple virtual sensor. On the other hand, multiple physical sensor can be taken as one virtual sensor. So the mapping is many to many. Next question is, dynamic caching mechanism improves the flexibility and efficiency of sensor cloud.
True,
True or
true.
false?
True. Option A.
Okay, anyone else? Okay. Yes, so correct option for this is true. That is A. Next question is, with respect to caching based architecture of sensor cloud, external cache has direct data connection with which of the following? Options are internal cache, user application, physical sensor. D is both physical sensor and internal cache.
It's option D, both physical sensor and internal cache.
Okay, anyone
Yeah,
else?
option B is the correct.
Right, option D is correct. So basically, this external cache lies between your physical sensor and internal cache. So the lowest layer is physical sensors, then external cache, then internal cache, and then user applications. Next question is, data from an IoT device is transferred to cloud by a network, which is then processed at the cloud, and then a response is sent back to IoT device from the cloud after processing. The time it takes for one way data transfer between the node and the cloud is 10 seconds. and data processing at time at the cloud is x second. It takes total 25 seconds for entire to and fro transfer of data between the sensor and the cloud with processing at the cloud. What is the value of x? Option A is 10 second, B is 5 second, C is 15 second, D is
It's
20 second.
option B, 5 seconds.
Option B 5 seconds. Option B 5
5
seconds.
seconds.
Anyone else? 5 seconds. Okay. Anyone else? 5 second, right? Because one way time is 10 second. So for sending request 10, getting response 10. So 10 plus 10 is 20 and the total time is 25. So the processing time will be 25 minus 20, which is 5 seconds. Next question is, there are two types of sensor data, A and B. A is time sensitive, that is required to be processed immediately, while B is not time sensitive and can tolerate longer time for processing. As per the standard utilities of cloud and fog computing, which among the following options show correct processing locations for A and B? Option A is A at cloud, B at fog, B is A at fog, B at cloud, C none of these, D both of these.
Option B, A, fog
Option
and
A.
B,
Option
cloud.
B, A
A,
fog
fog and
and
B,
B
cloud.
cloud. A fog and B cloud.
Yeah, it is a
A
great
fog,
point.
B cloud. Yeah, it is a great point. Okay. So anyone else? A is time sensitive and B is not. Okay, so since A is time sensitive, it should be processed near to your end devices. So A should be processed at fog and B at cloud. So correct option for this is B. Next question is, there can be multiple fog nodes in between the physical layer at the in between the physical sensor layer at the bottom and the cloud layer at the top. True or false? Anyone?
It's option A, true.
It's option A true. True. Okay. Anyone else? There can be multiple fog nodes in between the physical sensor layer at the bottom and cloud layer at the top. True or false? Twenty-eight A. Okay, so no one has replied for 29. Only one
Option A
person
is true.
replied. Option A is true. True, right. This statement is true. There can be multiple fog nodes present. Next question is, which among the following are a potential problem and challenge in fog computing? Options are power consumption, data security, reliability, or
All of
latency.
these.
All of these.
It's option D, all of this.
It's option D, all of these. Anyone else? Correct. It's option D, that power consumption, data security, and reliability, all these three are the challenges or problems with your fog computing. Next question is, OpenStack is a free open source software for cloud framework simulation and experimentation with various cloud applications. True or false?
Option A, true.
True.
True. Okay. Anyone else? Yeah, this statement is true. Next question is, which among the following is not a component of OpenStack? Options are origin, heat, plasma, neutron.
It's option C, plasma.
Okay. Anyone else? Anyone? Yes, correct option for this is plasma. Next question is, you cannot ping your OpenStack instance from an outside network unless you connect your instance with public network through a repeated question. Router, firewall, repeater, load balancer.
It's option A, router. It's a repeating question.
Right. Right, right. This is also repeated. So I'm skipping this, okay? Next question is, the SCSP in Sensor Cloud is responsible for caching the data in the databases. True or false?
True.
Anyone else? Yes, this statement is true. Next question is, select the correct option for replacing. Okay, so I guess this question is incomplete. The following architecture of Sensor Cloud. Yeah, this question is incomplete. Yeah, here is. Select the correct option for replacing the box in the red in the following architecture for Sensor Cloud User Organization View. So this is the red box. So what will be here? User credential, template display, template view.
It's
Next
option
question.
C, template view.
Template view. Okay. Anyone else? Anyone? No. Yes, template view is correct. So here the user from the browser the template view, no, so a user will send the template view, and on the basis of that the sensed information will be sent to the end user or application. Which among the following is the principal feature of Sensor Cloud with respect to sensor nodes? Options are sensor monitoring, sensor instantiation, sensor virtualization, sensor collection.
It's a repeating question. The correct option is C, sensor virtualization.
Right, sensor virtualization is correct. Next question is, caching in Sensor Cloud provide no benefit over region with slow environmental monitoring rate. True or false?
True, it is true.
True. Okay, anyone else? I'm repeating, caching in Sensor Cloud provide no benefit over region with slow environmental rate. True or false? this statement is false because if the environmental changes are less, then every time if you are getting the data from the sensors, it will consume their power and reduces their lifetime. So better to cache the data in that case, right? Because your environment is not getting changed every time. So the data which is sensed 10 seconds back will be the same right now. So it's better to cache the data in that case. So this statement is false because in such scenarios caching is useful. Next question is, how many different types of caching mechanisms are there in sensor cloud? Options are 1, 4, 2, 3. Anyone? How many different types of caching mechanisms are there in sensor cloud? Options are 1, 4, 2, 3.
Option C. Two.
2. Right. Two caching mechanism. One is internal cache and other one is external cache. Next question is, virtual sensor within sensor cloud have communication interface with? Options are only physical sensor below them. Okay, repeated question, so I am skipping this. Okay, this is also again repeated. In IoT, temporal sensitivity of data plays an important role. True or false? Anyone? In IoT, temporal sensitivity of data plays an important role. True or false? No? Correct option for this is true, because in case of IoT there are some applications which need processing in a very less amount of time, in fraction of seconds. However, there are some applications which can be processed over a large period of time, so it is temporal sensitivity is required in case. Next question is, extremely time sensitive data in IoT should be processed and analyzed blank, farthest away from the source, closest to the source, distance between the source and place of analysis does not matter, none of these.
Option B.
Option
B.
A. Okay, anyone else? Yes, so correct option for this is uh, B, that is closest to the source, because it is extremely time sensitive data, right? So the processing should be done near to the source only. Uh, because if it is done far away from the source, then there will be time delay, and it might happen that accidents may occur in within that amount of time. So it should be done near to your source. So correct option is B. Next question is, which among the following is a view of a fog computing architecture? Options are node view, system view, software view, all of these.
D.
B. System view. Okay. Anyone else?
Dog. All of these.
All of these. D. Right. Correct option is D. Next question is, which among the following is true? Okay, this is a repeated question, so I am just
Yeah,
repeating.
yeah.
Next question is, this is also repeated. OpenStack is free, open, so this is true. So yeah, these were the questions of this week. So those who have joined late, this is the link. I have already uploaded the PDF. You can access the PDF from this link. Okay. Any question? So we will meet again day after tomorrow. So okay. So that day I think we will discuss about smart cities. Okay, and some questions. So okay. If no question, then I am terminating the session. Yeah. Uh, you have any question? Jerry, you have raised hand. Do you have any question? Okay, if no question, then I'm terminating the session. Thank you.